So I'm going to tell you about special cube complexes. So Nir, I was lucky enough to hear you do the unpleasant job and field the questions so far. And Nir actually promised me that anybody that has questions about any of this material, they're welcome to go and speak to him about it and ask questions. So direct your questions to Nir. Okay. A covering space map is what? So I have, first of all, let's just talk about covering spaces of graphs. Remind you, some of you maybe are not used to this material. It's just a map that sends vertices to vertices and edges to edges in a very simple fashion that you imagine, which on top of that is a local isomorphism. Okay, so here are 5 different examples of covering space maps. I label and direct my edges, and you can use that in order to guess how edges map to edges. Okay? So these are infinite covering spaces. Here's one where the target B is not a bouquet of circles. Okay? An immersion of graphs is a combinatorial map, right? That's a map that sends vertices to vertices, edges to edges, which is also a local injection. Okay, so let's take a look at that and make some sense of immersions. Does this sound okay? Yeah, I'm okay. So here's an immersion. I'm going to favor bouquet of 2 circles. Capital B is a bouquet of 2 circles. I'm going to favor that because it's easier. As you can see, the idea is that there's at most one incoming edge and at most one outgoing edge of each label at each vertex, right? That's how you can recognize an immersion. And over here, it's not an immersion, right? At that vertex over there, you can see that there are 2 outgoing edges labeled with a single arrow, which I'll refer to as alpha for the single arrow and beta for the double arrow. Okay? So this is not an immersion. Yes, please ask.
What is
a combinatorial map is a map between graphs which sends vertices to vertices and edges to edges. What is a combinatorial map? It's okay? It's really very simple. It's not something fancy. Okay? Local isomorphism over here means how about like this? That at a vertex, at each vertex, you have an incoming and an outgoing edge of each type, right? So it looks the same locally over here as it does over there, right? So over here you see that there's an incoming and outgoing beta and an incoming and outgoing alpha. Right, and in the target at this vertex, there's an incoming and outgoing alpha and an incoming outgoing beta. Okay? So, I made up the numbers. Marshall Hall, I think in 1949, I used to care about the numbers, but I don't anymore, proved that when you have an immersion, I like to use this symbol over here for an immersion. When you have an immersion between 2 graphs, and the domain is a finite graph, meaning that there are finitely many vertices and edges. He showed that there's a finite covering space, B hat of B, such that the immersion from A to B lifts to an embedding in B hat. Okay, so I'm going to explain his construction, a very simple construction, and this will be very clear in a moment. So here more or less is the proof, right? Since A is finite, you have as many missing incoming alpha and beta edges as there are as many missing incoming as there are missing outgoing alpha edges, and as many missing outgoing as many missing incoming alphas as outgoing alphas, and as many missing incoming betas as outgoing betas. Okay, and because of that, what you do is you just choose a bijection between these sets, and you add edges to A and build B hat around A. That's all. So let's do that a couple of times just to get the hang of it. So here's my original graph is in blue. I guess it's that graph right up over there, right? So that's A. And now in red and green, I've indicated the missing incoming and outgoing red and green edges, alpha and beta edges. And you can count, right? You have this you have here there's two missing incoming reds and two missing outgoing reds, right? And three missing incoming greens, right? Those are the betas, and three missing outgoing betas. And I choose a bijection between the missing ins and missing outs of each color. And I connect them up, right? I add an edge, following the bijection, I add edges, right? So here are two ways of doing this over here. There are many ways usually between two sets. If there's a bijection between two sets, usually there are many bijections between those sets, right? So here's two ways, and you can see that I've built B hat around A, right? I've extended the map from A to B. I've extended it to a covering space of B. Right now, there's a at every vertex of B hat, it looks locally like B, so it's a covering map of B. Right. So it says over here there exists a finite covering space map. I wrote it as finite cover.
Oh, okay. You're going from immersion to cover.
Right. I started with an immersion, and I ended with a finite covering space. I made A bigger. B does not have to be finite, no. But you can try to see why A would have to be. Okay? That's a fun thing to try to do. So I discovered this myself around 1992 with great excitement, and it took me a while to realize that Marshall Hall beat me by a little bit, and I was involved in trying to do something that I'm kind of going to tell you about, and it was very important to me, and I identify with Marshall Hall very much. Actually, when A is connected, as it is over here, there's a retraction from B hat back to A. Okay, a retraction, it's just a map that from B hat to A, which fixes A. Right? You could think about why that would be. Every new edge that I've added, those are the thin black ones or the new ones. You just kind of smush them into paths somewhere. There are many retractions. Now, we study a free group. Free groups have come up already. We study free groups typically by thinking of them as fundamental groups of graphs, of bouquets of circles. Okay, and we can use Marshall Hall's idea, and it was used long ago to understand some nice things about subgroups of free groups. So a subgroup of a free group corresponds to a based immersion of graphs. So if you have a subgroup of a free group, here's three generators for a subgroup generated by three elements, and here are three based sort of loops that correspond to those three generators. You can see how, and you kind of fold them up a little bit to create this object A, which immerses inside of B, and the base point is right over there. And the fundamental group of A maps to this subgroup right over here. So this is kind of just to give you a suggestion of a construction that's very familiar for people studying free groups. So the immersed graphs correspond to subgroups in a nice way. Not quite a correspondence, but you get subgroups from immersed graphs and vice versa. And one of the nice consequences of Marshall Hall's theorem, which was something I was very excited about when I learned about it, is that every finitely generated subgroup is separable, which means that it's the intersection of finite index subgroups of the free group, right? So separable means it's closed in the profinite topology is a fancier way of saying the same thing. It may be a very simple way of, one-stop shop way of saying what it is that for any element little g which is not inside your subgroup, you could find the finite index subgroup K so that K contains your subgroup but doesn't contain the element. That's why it's called separable. Some people use the word LERF to mean that every finitely generated subgroup is separable. LERF is an acronym that stands for locally extended residually finite. No, the LERF property is related to this. That says that every finitely generated subgroup is separable, and I just defined separable, so it's just related. I'm not a fan of acronyms. LERF is locally extended residually finite. Okay, locally means every finitely generated subgroup has the property. Extended residually finite, you understand. No, Alex, no. I defined separable. Sometimes you can study a subgroup and say it's separable, but the whole group might not be LERF. It's not that often the whole group is not LERF, right? The whole group is not subgroup separable is the other term for it, right? But a specific subgroup that you're interested in will be, okay? So so it's actually important to distinguish between them. Okay, so for the trivial subgroup, it's separable. That's the same thing as the group being residually finite, right? Which means that every element survives in a finite quotient, is non-trivial in a finite quotient. And let's actually see let's see that free groups are residually finite. Let's see that the trivial subgroup is separable, right? So if you have, let me sketch the proof. If you have an element little g which is not the trivial element, then you could think of that element g. You could represent it by a non-trivial reduced word like alpha beta beta alpha inverse beta inverse. Okay, and you make a little picture of it. Here's the picture of alpha beta beta alpha inverse. Okay, I made a typo, so it's a different word. Alpha beta beta alpha inverse beta. Okay, never mind. And you take that, you think of it as an immersed graph, just as we were doing before, and you complete it to a covering space of B. Here I've completed it by adding these green edges. And what you've done is you've created a finite covering space of capital B with the property that the element little g that you're interested in does not lift to a closed path in this covering space. And what that means is that little g is not in the fundamental group of this covering space B hat. Okay? So, and you've succeeded in separating little g from the trivial element in that fashion. Okay? And more generally, you can show that every finitely generated subgroup of your free group is separable, and you follow basically the same idea. If you have an element little g which is not in your subgroup, then what that corresponds to is you could think of your element little g as represented by a word w, which is not a closed-based path inside of a graph. So you have the graph A that corresponds to your subgroup, and your word w, or your element little g, corresponds to some green path over here, which doesn't close up. So here was the start point, but the end point is different. And then you use Marshall-Hall's theorem, and you add the missing edges to create a finite covering space, B hat. And now you found a covering space B hat such that the fundamental group of your covering space contains contains H because it contains this graph A as a subgraph. But the element little g is not inside. Okay, so this is a proof that every finitely generated subgroup of a free group is separable. That's what you call the LERF property. Now, actually you get a little bit more. What you get is that since A is a retract of B hat, you get that every finitely generated subgroup is a retract of a finite index subgroup is a retract of a finite index subgroup pi 1 B hat of your free group.
What is retract in this?
A retract in any category means the same thing.
So tell me what it is.
It's a map. It's a map that a retract to The sub-object is a map from the object to the sub-object that fixes the sub-object. So back in the day, when I was thinking about this and I had a certain agenda, I actually cooked up a slightly different version, what I called canonical completion and canonical retraction. It's a specific way of extending your immersion to a finite covering space. Let me just show it to you. It's very simple. What you do is you extend each maximal alpha path to an alpha cycle, and likewise for beta paths, you extend them to beta cycles, right? So let's look at that in this picture. So look at this maximal red path right over here, right? You can add one edge to turn it into a red circle, right? And similarly here, this red path right over here, I can extend it to a red circle, right? And this green path over here, length to green path, I extend that to a green circle by adding just one edge. I directed it the wrong way. You see that? Made a mistake. Okay? But you guys haven't pounced on me altogether because I noticed it first. Now, look at this one over here. Here the path was just the trivial path, and so when I extended it to a cycle, I'm just adding a loop. Okay? And maybe there was already maybe it wasn't really a path. Maybe it was already a cycle. In that case, you just leave it alone. Okay? That's canonical, no? It's my version of canonical. And what do you think the retraction map is? Well, the new edge that you've added, you smush it down to the path that it corresponded to. So for instance, I had this red path over here, and I added this red edge. And my retraction sends this new edge to the path that it was completing.
But how do you know if it was like an original one?
If it was already there, then I leave it where it was because it's a retraction.
Oh.
Right. Okay, perfect. So here I add this loop. That's even easier. See this loop? I smush it to a point. If that's a new, you want to look back over here? Here, you want to look, imagine, where does this new loop go? It gets smushed to that point. Where does this edge go? It gets smushed to there. Where does this edge go? So, notation is very important. So, I call, instead of calling it B hat like I was doing before, I call it the canonical completion of the map from A to B. You see that notation over there? That's all. Okay, so get used to it. And I didn't explain to you how this goes when B is not a graph. I just told you when B is a bouquet of circles. Bouquet. So you're all hypnotized. Good. So when B is not a bouquet of circles, I just explained to you when it's a bouquet of circles. So what do? You create a bouquet of circles by identifying all the vertices. Right? You quotient B by identifying all the vertices to the same place. No, you don't do that. That's a terrible thing to do. Okay? You should never do that. Okay? You identify all of the vertices to one vertex. Okay? And now you do have a bouquet of circles. Call it S, unfortunately. Okay? And now you do the following. So I have my map from immersion from A to B. Well, A now immerses inside of a bouquet of circles. Right? Because I didn't contract a spanning tree. Okay? And so now there's a notion of canonical completion of the map from A to S. We've just spoken about it. And then you just take the fiber product of this canonical completion, right? This covering space of S, and the map from B to S. And that's your fiber product right over there. And you define the fiber product to be the canonical completion of the map from A to B. Okay, so I better say what the fiber product is, right? Okay, but it's something that I'm sure you all know, that you've seen in some fashion. So when you have two immersed graphs from P to B and Q to B, then the fiber product of P to B and Q to B is right here. It is the fiber product. It's this. It consists of its vertices are pairs of vertices that map to the same place in B, and its edges are pairs of edges in P and Q that map to the same edge in B. Okay, and here's a picture, right? So you've probably seen it before. right? Maybe when you were thinking about finite state automata or something like that. All right, so the motivation. What was the why was I thinking about all of this? It's a very long time ago. I've hardly changed, I must say, but the world around me has changed a little bit since then. So I was interested in understanding residual finiteness of groups. I would take of course I thought about the simplest thing that I didn't understand. Right, the simplest thing that I didn't understand was a group like this. It's called an H&N extension, a very, very easy H&N extension. But never mind, you could see it's a presentation. There are three generators, alpha, beta, and T conjugates some word of length 4 to another word of length 4. Okay? And I like to think about it like this. I like to think of it as the fundamental group of this complex that you get, of a 2 complex that you get by taking a bouquet of 2 circles labeled by alpha and beta and attaching a cylinder to it. And the left side, the one side of the cylinder gets attached along the path alpha, beta, alpha inverse, beta inverse, and the other one gets attached along the path alpha, alpha, beta, beta. Okay? And, well, everybody knows about non-positively curved cube complexes, but nobody knows about non-positively curved square complexes, right? Did you mention them? Those are 2-dimensional non-positively curved cube complexes. Okay? Yeah? So this is a non-positively curved square complex right here. How so? Well, you have to divide the cylinder into 4 squares, as I've done. And you could check that the links are flag complexes. Okay, that was the way you described the condition? Yeah? Yeah. Okay, so.
Four squares and not 2? I don't see, like, maybe I'm missing something.
Yeah, you see that when you see that there were already 2 black edges over there?
You use them?
I'm using them.
Okay,
Okay, great. And the 4 edges correspond to the 4 squares correspond to the 4 edges that you see over here. Right? So it makes sense. So what was I interested in doing back in the day? So I wanted to understand residual finiteness of objects like this. And that's what led me to think about canonical completion and retraction. So a non-positively curved square complex is called clean if it's a graph of spaces. This might be new to you, but you'll catch on very quickly. It's a graph of spaces with vertex spaces are graphs, the edge spaces are graph cross edges, and the attaching maps are injective. I'm sorry that I'm using the word graph too many times, but you guys like graphs, right? Huh? It was in the Institute for Advanced Study that I asked, are there any graph theorists over here? I was harassing a bunch of topologists at that time. And one guy raised his hand and said, I'm a graph theorist. And introduced himself to me later on when I asked, okay, who are you? And he said, Avi. So I figured, okay, this guy must be pretty serious if he's just Avi.
No last name.
But now, Dani. There. How did this happen? Elite. Anyway, and after my talk, I must say, I went home and I got a beautiful email telling me how to generalize my talk. So thanks a lot. Okay. Let's stay on topic over here. A non-positively curved square complex is clean if you can break it. So here's an example. I'll explain it by way of an example. It's you can build it by taking a graph, by taking a few graphs, right? There's a graph blueprint. There's a graph for every vertex, right? Here they are. And then there's a graph cross interval. Here's a graph cross an interval that I'm attaching, right? Here's another graph cross interval that I'm attaching, and I glue them on. Okay, I require that the attaching maps be combinatorial embeddings. Okay, those gluing maps. And here I've built a complex with how many squares? Let's just count the squares so that we see that it's a square complex at least. So I can see 2 over here because of the edges that I'm using, right? And then 3 over here, and 1, 2, 3, 4, 5 over here. Okay? So everybody see this is a complex with 10 squares?
Well, 5, how are they?
Well, 1, 2, 3, 4, 5 edges over there, and it's I took a graph with 5 edges and I crossed it with an interval. I get 5 squares. Okay? And I glued them all on, and you could see that all of the gluing maps are embeddings. Right? Yeah, can you see the gluing maps? Are the colors clear enough so you can see the gluing, so you can understand what the gluing maps are? I think so. Okay? And I called this a clean square complex, or clean graph of spaces. It was a clean square complex. And the meaning of my life, honestly, the entire meaning of my life was to understand clean complexes. I thought that was it. If I could just understand clean complexes, or if I could take a complex, like this one over here, right, which is not clean, because you could see that these attaching maps are messy, twirl around somehow. They're not embeddings. What I wanted to do was to find a finite covering space of this, which was clean. Because if I could find a finite covering space that was clean, I could use that to understand many nice things about the complex. Let me say it like this. It's easy to build finite covers of clean complexes. That's what I understood. And my strategy for understanding a square complex, a non-positively curved square complex, was to find a finite clean covering space. If I could do that, then I could understand it from certain viewpoints, right? And my understand for me was have the power and control, be able to create finite covering spaces, because I'm interested in finite covering spaces. I'm interested in residual finiteness. Okay? So, and it was the properties of canonical completion and retraction that I was using in order to create finite clean covering spaces. And that's why I cooked up that special case of Marshall-Hall's theorem. Okay? Now, you might hope, and I might have hoped also, I did hope, that, since non-positively curved cube complexes generalize graphs, that's very arguably true, right? They're just higher dimensional versions of graphs. You might hope that Marshall-Hall's theorem, which lets us create covering spaces so easily, actually generalizes to cube complexes. And the answer is no, it doesn't. It's just, cube complexes are not so easy from this viewpoint. They're very easy from many viewpoints, and they're wonderful, but they're not quite right as far as, they're not quite faithful generalizations of graphs from the viewpoint of things that are helpful for understanding free groups. Okay? Certainly algebraic things that are helpful for certain things. Well, so instead there's something called special cube complexes, which are special cube complexes. And they generalize graphs, and in particular they have a canonical completion and retraction. And so with Fredrik Haglund, my beloved collaborator, we figured out the non-positively curved cube complex. We figured out the property of a non-positively curved cube complex, which we called special, which lets you do canonical completion and retraction. Okay? And here's the property. It's expressed in terms of the hyperplanes, the immersed hyperplanes that Nir told us about. And it's quite simple. You just list the things that you don't want it to have. You don't want it to have self-crossing hyperplanes. You don't want it to have Möbius strip-like one-sided hyperplanes. You want every hyperplane to have a kind of product neighborhood. You don't want it to have self-osculating hyperplanes. That's this weird thing over here, where the hyperplane comes right up close to itself. This red hyperplane comes close to itself somewhere, right there, that vertex, but doesn't cross itself. And you also don't want it to have interosculating hyperplanes. These are two hyperplanes that cross in one place and then osculate in another place, right? What does osculate mean? It means that they come up close to each other over there, but they don't cross. So there isn't a green square that have them cross right there. As it happens, any graph is immediately special because there's not much that can go wrong for graphs. And actually, any subcomplex, if you take the Cartesian product of two graphs, you get a non-positively curved square complex. And that actually is special as well. It's fairly easy to check. And in fact, back in the days when clean was the meaning of my life, one of the things that I knew about clean was that if you're clean, then you have a finite cover, which is a subcomplex of the product of two graphs. Okay? So I knew that clean and was almost the same thing, as it was very closely related to this. Any cat-zero cube complex is also special. Right? The hyperplanes, they kind of go off in different directions. They never come back to crash into each other because of local isometry type ideas that Nir alluded to. Okay. Here's an example of a special cube complex that I built just for fun. Okay. I'm not going to check though. Now, let's start to get things moving. A combinatorial map of cube complexes, it's like a combinatorial map of graphs. It sends cubes to cubes. It sends 0 cubes to 0 cubes, 1 cubes, edges, 1 cubes to 1 cubes, and so forth. Okay? And a local isometry of cube complexes it's a local injection with the additional property that whenever you have two 1 cubes, E1 and E2, at a 0 cube, if their images form the corner of a square, as I've indicated over here, then they have to already form the corner of a square in the domain. Okay? That's a local isometry. There's various ways of expressing it. This is the simplest one because we already know that A and B are non-positively curved. Okay? So long as you're in a local injection, you have this property, you are a local isometry. And there's an easy lemma that says that whenever you have a local isometry between two cube complexes, then the associated map, if you lift that map to a map between their universal covers, it's actually an embedding. And it's actually an embedding as a convex subcomplex. And because of that, local isometries give you pi1 injections. So if A maps to B by a local isometry, pi1 of A maps to pi1 of, the map from pi1 of A to pi1 of B is an injection. Okay, it's a very nice injective map on the fundamental group. That strange property of being special, right, which is the property that lets us do canonical completion retraction. I didn't quite tell you how, I will in a moment. It actually, within like a half an hour of, sort of working out what we wanted special to be, we were very disturbed because we noticed that being special meant that there was a local isometry to a Salvetti complex. Remember, Nir told us about very, very easy examples of non-positively curved cube complexes. You take a right-angled Artin group, you take a bunch of generators, and you make some of them commute with each other. And there's an associated cube complex, right? You add a cube, you add an n cube for every collection of n pairwise commuting generators, right? And in that way you form what was called the Salvetti complex. Well, what we noticed was that being special was the same thing as admitting a local isometry to a Salvetti complex. And so maybe I'm not going to spend so much time on this. I mean, I'll rush through it very quickly. Why not? So a Salvetti complex is special. All the good cube, non-positively curved cube complexes are special. Okay, I said the cat-zero cube complex is special. Graphs are special. Salvetti complexes are special. And if you have a local isometry from y to x, and x is special, then y is also forced to be special because the pathologies that we don't like, they project to pathologies. On the other hand, maybe this is interesting. Yeah, this is very interesting. On the other hand, if you're special, let me explain. If you have a special cube complex, this is a special cube complex over here. Let me show you how you get a local isometry to a Salvetti complex. Okay, it's fun. So you take your cube complex and draw in the hyperplanes. Here they are. There are 6 of them. I've colored them all. And you create a graph, gamma, which is just encoding the hyperplanes and which ones cross. So the first and the second, here's the first hyperplane, it's right here, it crosses with the second hyperplane, which is over there, right? The fifth hyperplane, which is, the fifth hyperplane, the blue one, crosses the second one and the sixth one, right? Because of the red and the green. The blue one crosses the red and the green and so forth. So you get what's called the, maybe the hyperplane crossing graph, gamma. Now, associated to any graph, gamma, there's a Salvetti complex. Here it is. And here's the associated presentation, right? I have a generator for each of the 6 vertices of my graph, and 2 generators commute if they're adjacent to each other. And actually, it will add a 3 torus whenever there's a collection of 3 pairwise commuting generators, right? 3 pairwise crossing hyperplanes. And in that way, I've created a cube complex, right? I've just shown you the cubes inside of it. You have to glue them together, and you have to check that it's really non-positively curved, but Near proved it. Okay? Now, the map from X to S is pretty reasonable. You see, when you've drawn in these hyperplanes, that it tells you how to label and direct the 1 cubes, right? All of the edges which are sort of dual to the red hyperplane, to hyperplane number 2, they get a red label, all consistently directed, right? We're using over there some of the properties, right? We're using that the hyperplanes are two-sided in order to know that you can you can choose the orientation of those edges in a well-defined fashion. Okay? And the various other properties also ensure that you actually get a legitimate local isometry from X to this Salvetti complex. Okay? What's the map? Well, all the vertices map to the vertex. All of the 1 cubes map to the corresponding 1 cubes with the corresponding directions and labels. The squares map to this squares. There's only 1 square with a given pair of labels. The 3 cubes will map to the 3 cube, etc. Exactly using the labels. That tells you how to do the map. So you get a nice corollary, which is that if you're special, then you're actually the fundamental group of a right-angled Artin group. Okay? Now, if you're a special cube complex, you have a canonical completion and retraction. So how does that generalize? Well, if you have a local isometry from some other non-positively curved cube complex y to X, then there's a finite cover of X, X hat, which is the canonical completion of the map from Y to X, and there's an embedding of Y into this canonical completion, just like we had in the case of graphs. And there's also a retraction from X hat back to Y. Okay, so the thing that we did with graphs that was just a silly doodle of just adding a few edges in a kind of natural fashion, it generalizes to these special cube complexes, right? Something that you really can't do. If someone gave you a cube complex and said, okay, try to build a covering space, you wouldn't know how, and you probably wouldn't be able to create a non-trivial covering space, but you can do it with tremendous ease for these special cube complexes. We restricted ourselves tremendously to a very, very specific subclass of cube complexes, these special cube complexes, which are very rare. Most cube complexes are not special, right? So that it's very rare. Here's the construction that you're asking about. Wait, how does this work? So here's an example, right? Here's a cube complex X, and it's special. Here's the associated Salvetti complex, right? You could see it's one skeleton. It's just a bouquet of circles. And here's here's a complex that maps by a local isometry to X. It's disappointing because the complex Y is just one-dimensional, and it's even not very interesting from the viewpoint of the fundamental group, right? It's just an arc. But I promise you, this is the easiest interesting example that exists. Okay, if you make a larger example, then everybody will hate me. Okay, so this is a very easy example. So here's my local isometry from Y to X, and what you do in order to create the canonical completion from of Y to X, right? This is what we want. I can't. Don't look at this. So we're interested in this commutative diagram right over here. Right? So this is what we're interested in creating, this canonical completion. Right? What you do is something very similar to what I told you before. You focus on the Salvetti complex associated to X. The Salvetti complex associated to a graph, by the way, is what you get when you identify its vertices. Okay? And you look at its Salvetti complex. Now you have a map from Y to the Salvetti complex just by composing. And well, you could look just at the one skeleton of the Salvetti complex. That's just a bouquet of circles, right? So now I have a map from the one skeleton of Y, right, which happens to be Y in this case, to a bouquet of circles. I know how to create a canonical completion over there because we discussed that already. It's a very, very easy algorithm, as you called it. And then you take then by a quick check, you can see that because of the properties of special, you can add squares, right, to get an actual covering space of S. And then you do what we did before. You take what's called a fiber product in order to create this. So here's the canonical completion of Y to S. You take a fiber product with X in order to create a canonical completion of Y.
So is there a canonical way to add these squares? I mean, the addition of the squares is also done in a...
This is entirely canonical, following a recipe. I prefer a recipe to algorithm.
But am I supposed to understand what the canonical way is from this drawing?
If you studied this carefully for 6 minutes and 30 seconds, I think you'd get it. Okay? So I'm going to continue now. I think that my purpose over here was to, A, tell you that there is this thing, canonical completion, and then to show you one picture to sort of give you a feeling about how complex a recipe it really is. It's not that bad, but you need to have some level of comfort with fiber products, and then you have to be willing to deal with someone else's horrible notation and make it your own. But it's always like that. Okay? So I'll move on. Now, what are the rules over here? It says 5:46. Does that mean I have 45 seconds left or 5 minutes and 43 seconds left?
You have more than 5 minutes.
I have 5 minutes and 37 seconds. Okay, got it. So, X, a cube complex X is virtually special if there's a finite covering space, x hat of X, with the property that x hat is special. So here's an example. Here's a cube complex. 2 dimensions is fine. It's good enough for really to understand the behavior. My intuition is really only 2-dimensional. What's great about cube complexes is that you can reach into very, very high dimensions with a pretty low dimensional intuition. Here's a cube complex which is not special, right? You can see that there's interosculation. So these 2 hyperplanes interosculate. They intersect in one spot and they osculate in another. And I think I got this right. Here's a covering space x hat of X, which is special. Okay? You have to check. You have to check all the things, right? You have to check that all the hyperplanes are two-sided, that there's no are two-sided, that they're not self-crossing, that there's no self-osculation and no interosculation. But it's good. It works. So sometimes you can take a cube complex which is not special, and find a finite covering space, which is special. And then you celebrate because I claim it helps you to understand it. Here's another example, just for fun. It's not really for fun. I thought I'd work this one out, but then I decided it wasn't a good idea. But you guys are probably hopefully getting it, and some of you maybe can think about how to make a finite covering space of this, which is special. Right now there are two problems. There's interosculation. There's also self-crossing. Right? Can you get rid of both of those problems by taking a finite covering space? You certainly can. Okay. And here's another example. Here's a cube complex. It's a square complex again. It's just two-dimensional, right? You know what object is homeomorphic to this square complex? It's surface. Yeah? Genus to surface. Yeah? Right? Yeah, you recognize it? Huh? Thank you. It's genus to surface. It's genus to surface, right? Yeah. You understood what I said, right? Okay, good. I didn't understand it, but I'm starting to get there. After welcome to Israel. I'm starting to understand you guys now. This genus to surface has a.
How do you see it? Why is it so clear?
Because I've done it so many times. I can't see it. I'm just an incredibly good actor. I can't see it, but I've worked through it many times, and so I know it already. Okay, and then I pretend. So, this has a finite cover. It has a degree 4 cover, which I haven't fully illustrated, which is special, right? You could try to guess how to build it. It's not. It's kind of right. I could have given a little more of a hint, like it would look something like this. Here's what I left out. So here's the covering spaces of the. You build covering spaces of the vertex spaces, and then you attach covering spaces of the edge spaces in a compatible fashion. So maybe I'll just do right. The 4 edge spaces will be copies of this one edge space over here. This is a picture. Maybe I didn't make it clear. It's a bouquet of 2 circles, and a cylinder that gets attached to it. But the cylinder has been divided into 4 squares. Okay, maybe that's the extra information that you wanted. So yeah, I got it. So what's the takeaway over here? The takeaway is that many non-positively curved cube complexes are virtually special. They might not be special, but many of the cube complexes that Nir sort of kind of suggested how we might build. You might get them. Maybe you build them from by studying robots. That's one of the ways that people make cube complexes. Some configuration spaces, or maybe you got them by some type of algebraic tricks with wall spaces, or maybe you got them from people studying median spaces 100 years ago. Many of them are virtually special. They're not special, but they have finite covers that are special. So, for instance, all the cube complexes that arise from Coxeter groups are all virtually special. It's one of the very interesting things. So we know, for instance, that every Coxeter group, right? We heard about finite Coxeter groups, but there are lots of infinite Coxeter groups. They're mostly infinite. Time is up. Many non-positively curved cube complexes are virtually special, and what happened is that this provides a bridge from geometry and topology in the fundamental group to algebra and right-angled Artin groups. And it's been very successful, and maybe there's a lot more to do. My time is up. Thank you so much for listening to me.